Hi, I'm Rasmus Nielsen from RUNSAFE. In this video, I will discuss how to pose an appropriate causal research question within running injury research. A warm welcome to all of you. This video builds on a previous video where we discussed why we wanted to investigate why injuries occur. This information is crucial in order to identify suitable preventive interventions. So in this video, we wish to assist runners, clinicians and coaches to understand what training advice program works best for whom and under what circumstances. This is what RUNSAFE intends to do with data from the Garmin-RUNSAFE running health study. Please continue and allow me to explain why. This presentation is based on a recent publication in British Journal of Sports Medicine from 2020 exploring the too much too soon theory. And it also builds on some of the recommendations from the past 10 years. In a publication by Soligard, it says there can be no one-size-fits-all training or competition program. Ultimately, the time frame of recovery and adaptation, and hence susceptibility to injury, varies within and amongst athletes. I fully agree with this, and consequently we need to consider our causal research question carefully. For instance, do we want to provide the same advice to all athletes, all runners? Maybe for some types of sports injuries that could be okay to prevent certain sports injuries. For instance, if these were cyclists, we would recommend all of them to wear a helmet in order to reduce the risk of trauma. So in this case, we want to recommend everyone to wear a bike helmet. Same advice to everyone. But imagine what would happen if we copy-pasted the same thought to training load. Should we recommend everyone, regardless their size and shape, to run in a similar manner? I don't think that would be appropriate. And in our article, we discussed different types of research questions and their link to sports injury prevention. And there are 4 different types of causal research questions. Number 1 and 2, links to population-based prevention. Here, we want to provide the same advice for everyone. Whereas the latter 2, number 3 and 4, is personalized athlete-specific prevention, personalized in the sense it's a subgroup of runners that we want to provide advices for. So different advices to different subgroups of runners. And here I argue that the first 2 causal research questions are irrelevant to our research if the target is to provide different runners with different advices. Let me provide an example and explain why. This is very simple and also too simple to be causal, but in order to illustrate my train of thought, I think this example works nicely. So we have a running distance exposure, either the population run 10 kilometers or 15. Then our outcome is running related injury and the confounder is type of population. I apologize for the runners in the Garmin-RUNSAFE running health study. This is a little technical, but I hope you can proceed and I will explain on what a confounder is. So the confounder is 3 different types of populations, population A, B and C, or we could frame them otherwise. A is the recreational runners, B are the experienced runners, and C are the novice runners instead. So if we want to make public health prevention and recommend everyone to do the same, then we could make an analysis where we want to investigate just the association between running 15 kilometers and running 10 kilometers. So say that the risk of injury amongst those running 15 kilometers is 16% and the risk of injury amongst those running 10 kilometers is 5%. This equals a risk difference of 11 percent point. If we then use the concept of confounding and adjust the result for a type of population, we'll get a risk difference of 8% instead. This is usual practice in many scientific articles to include additional variables in the analysis as confounders. As you can see, in this case, it also changes the estimate from 11 percent point to 8 percent points. So, how would we interpret this? Well, the 8% are interpreted as follows. There are 8 percentage points fewer running injuries amongst those running 10 kilometers than those running 15. This reduction is assumed to be similar in all 3 populations. So the reduction is likely to occur both in the recreational runners, the experienced runners, and the novice runners. But is that the case? If we look at the figure, the green is representative of the safe zone, where the injury risk is low. Yellow is the medium zone, and red is the high risk zone. And we can see on the graph that the population B, the experienced runners, when they run the 15 kilometers, they are in fact in the green zone. Whereas the novice runners running both 10 and 15, both populations are in the red zone. So possibly the advice of changing training load to the same extent in all 3 populations is inappropriate. It may be appropriate for population A, the recreationals, because they transit from a red zone to a green zone, and that might really be appropriate for that population. But for population B, the experienced runners, advising them to reduce from 15 to 10 would be highly inappropriate, because they are able to tolerate 15. Why then recommend them to reduce to 10? And population C, the novices, well, it's not sufficient to recommend them just to reduce to 10. They should be recommended to reduce to below 5 in this case. So the reflections would be that population B, the experienced runners, do not harvest the health benefits of more running. And population C still run too much. They need to reduce even more. So but just using population as confounder is an advanced analytical concept, I know, but I hope you get the point here that we may recommend some subpopulations to do something that's inappropriate for them while using that concept. So if we use another analytical concept instead, called effect measure modification, and that's what we intend to do in the present project, we may get different results. So let's say that the risk amongst the population A running 10 kilometers is 7% and 29% amongst those running 15. The risk difference is 22 percentage points. That's rather huge, but remember they come from red zone to green zone. Nothing happens in population B, the experienced. They have 6 percentage point risk of injury in 10 kilometer zone, and also 6% risk of injury in 15 kilometer zone. So there's no risk difference amongst those running 10 and 15. And even though we see a 7 percentage point reduction from 36 to 29 in the novice population C, 29 is still rather high. So, is it really appropriate to recommend everyone to reduce? If we do so and use confounding, we assume the risk difference is similar. We assume that 22, 0 and 7 is identical, and it's not. So that's why we want to use effect measure modification instead. We want to analyze what works best for whom and under which circumstances. The downside of doing this is that we require a lot of data, and this is a very technical article on how to analyze data in a very detailed way. But the intention with the slide is to highlight that we need a lot of data in order to make such analyses. Fortunately, we have a lot of data in the Garmin-RUNSAFE running health study, and you assisted collecting it. So we are so positive, and we hope to be able to explore better than done previously how different runners should schedule their training in order to be at low risk of injury. So basically, what this presentation is about is a little technical, but to highlight that the concept of confounding is not really valuable if we want to provide different advices to different persons. So in order to make subgroup specific recommendations, we need other analytical approaches, and in our case we use the concept effect measure modification. So I hope this video highlights the need to clearly consider the analytical approach in running injury research, because we believe it's very, very necessary in order to examine why running injury occurs in different types of runners. These causes are likely to differ, and we need to take that into account.